Good morning, everyone. Welcome back after a nice spring break, I hope. Quick recap of what's happening so far, as you hopefully did get my email. Um, the worksheet from Chapter 4 can be turned in at your earliest convenience, and that will be your really only grade that we'll have through the Chapter 4 topics. Remember that I did send a new calendar, so refer to that as much as you'd like. We'll try to stay on that kind of pattern of a video, day of work. Email me with questions. I can put together a solution video if it may help. Just make sure that if you have any trouble accessing the materials, getting the materials to me, or accessing the videos, that you let me know. And I'll take care of things as soon as I can. Well, today we're going to make a big switch in what we're working on. And the best way I have to compare it to is, back in elementary school, you first learned how to multiply two numbers. 3 times 4 is 12. Very simple. Well, before too long, you had to look at the number 12 and think about what two numbers would multiply to equal that number. And of course, you knew the factors were 3 and 4. Then in Algebra 1, you were expected to multiply binomials, maybe x plus 7 times x minus 5. And you had a trinomial. But then soon after, you were expected to look at that trinomial and break it apart into two pieces, two factors. Those reverse processes is something very common in mathematics. The reverse process of differentiation, which is what we've been working on this whole semester, is quite simply anti-differentiation. We have other words for it and other uses, but at its most basic level, that's really what we're going to be doing. So, for example, if I just put this on the board and I ask the question, if the derivative of some function is 3x squared, what is the original function? Well, just knowing something about differentiation, we should be able to come up with that. And I'd love to have you here and ask those questions and see what you come up with, but hopefully you would realize that the function would have to be x cubed. Or maybe not have to be, but could be. Because if you would then find the derivative of x cubed, you would get 3x squared. But then you start to hopefully notice that what if it were 3x cubed plus 2? It would still have a derivative of 3x squared. Or it might be 3x or x cubed plus 6 or 5. Same thing. So what we do, because the answer is not going to be a unique answer, is we just put a c, and the c stands for some constant, because we know the derivative of that constant would end up being 0. So this is one of many answers, but with the plus c, we pretty much account for all of these answers. Now there's some different notation that we might have for this anti-differentiation. One is that I could say y prime equals 3x squared, and therefore y is x cubed plus c. Really the same idea. I could say that dy dx equals 3x squared, and then of course y is still x cubed plus 3. So just like with differentiation, where we could ask you to perform differentiation in a variety of ways, that's going to happen here in anti-differentiation. I could give you the derivative and ask you what the original function is in a variety of situations. Now there is one other option, and that other option involves this word, integration. And that's actually a more common option. We tend not to say anti-differentiation for too long. It's nice early because we really know what we're trying to find. With integration, what we do is this. We kind of think of a function that has a derivative in it. dy dx equals 3x squared. And then we think of the dy dx as a fraction. It's basically a differential. You might remember that you found in the end of chapter 4. So I could write dy would equal 3x squared dx. Now, integration comes into play when we try to undo the derivative. and we have a symbol for integration. It's basically a squiggly mark. It means sum that we'll get to later, especially if you take future courses. But I am going to find the integral or antiderivative of this function and the antiderivative of this function. Well, we know that if we do the same thing to both sides of the equation, it should remain true. So in this case, the antiderivative of 1 with respect to the variable y is y. The antiderivative of 3x squared with respect to the variable x is x cubed. Then, of course, we have our constant. So it seems like something that makes things more complicated than they have to be, but formally, when we talk about integration, we're really trying to find that y value. We're integrating the function, we're finding the antiderivative. Many students will ask, well, what do I do with this dy and this dx? Really nothing. It's notation. This notation means, again, the integral or antiderivative of the 1 with respect to y. Here, we have the antiderivative of 3x squared with respect to x. So it's just notation. We never really do anything with it. So that's basically what integration is all about. Now, there are a variety of rules that we could use to find integrals much more efficiently. For example, let's say we have this function. The integral of 2 over radical x. Well, this was easy because we could just see it and play with it. But eventually that falls apart pretty quickly. But never forget, that's really what you're doing. If I want to integrate 2 over radical x, it might be nice to put it in a form that we've seen many times. That's the same thing as 2x to the negative 1/2 power. So again, this is what we call the integrand. It's what's being integrated. Now, if we think about how it really happened back here, if integration and differentiation are inverse processes, you have to kind of undo what the other one did. Meaning, in differentiation, the exponent became the coefficient. Then you took 1 away from the exponent to get 3x squared. But in the other direction, you're going to want to add 1 to the exponent to make it a 3, and then you got to divide by that 3. So basically what we can have here is an answer of, if I add 1 to this exponent, that becomes x to the 1/2. And then I divide by that new exponent, I end up with 4x to the 1/2, of course, plus c. The great thing about all integration problems is we can basically check it. If I want you to find the derivative of this function, 1/2 times 4 is 2, x to the negative 1/2. Now, formally, what this ends up leading to is something we could call the power rule. The power rule gives us a way to integrate x to the n power. And simply stated, it's just add 1 to the exponent and divide by the new exponent. Now, there's only one thing about this. It's not true for a certain value of n. And that value of n is negative 1. So n cannot equal negative 1. All right? Well, let's do a couple more just to see what you come up with. If I wanted you to integrate e to the x, well, the integral of e to the x, we should just know, is e to the x. The reason being is the derivative of e to the x is e to the x. Not much to that. What about this one? The integral of 1 over x. Well, you might want to do the same thing I did in this previous example and change it. But then that becomes x to the negative 1. This power rule will not work when n is negative 1. But if you really think about some of the derivatives that you know, The only option for this to be true is that if it's the log of x. Why? Because the derivative of log x is 1 over x. So the integral of 1 over x is log x only because the derivative of log x is 1 over x. So many times it's that anti-differentiation process that gets us to where we need to be. Other times we are going to be a little more formal with this power rule. On page 286. Page 286, there's a whole list of rules. And we would talk about them if we met in a normal class situation. But you can read that, study them. It's basically all of these plus some of those involving trig functions. One last example. What if we were to integrate cosine of x? So in other words, what would the antiderivative of cosine be? Well, without too much trouble, you would realize that it's a sine of x. Reason being, the derivative of sine is cosine, so the integral of cosine is sine. So, for the rest of Chapter 5, we're basically going to be finding this thing we call the antiderivative, or maybe more conveniently, the integral of functions. There are many, many uses and applications. We will touch on a few, but in this course, we won't study as many as we would compared to what we did with the derivatives. This is part 1. There is a little bit more we have to look at in this section 5.1, but I'm going to pause it now. I'll upload this as a separate video, and then I'll come back soon with part 2 from section 5.1.